Sorry about that. So I was talking about a process-based morphological model. Again, I said very fast. We have an initial model passed to the hydrodynamic model. Hydrodynamic model calculates the flow patterns. And then on top of that, we have sediment transport patterns calculated. Obviously, when we have a sediment transport model, we can have erosion, deposition. So the initial bed level that we had in the model will be updated. So that updated bathymetry can be passed to the next time step. And we can continue this cycle over and over again and even forecast the future. So that's the meaning of a process-based morphological model. So here we are showing some examples of the model. This is Atchafalaya Delta. This is a very short animation because I got the output every 5 minutes. So it took time for me to even make this short time animation. Anyway, we are seeing here flow velocity. And obviously, this animation is not going to give us that much information. We need to have current vectors so that we have an idea that what's the flow direction. And as we can see, mostly in this system, flow direction is from upstream to downstream. Just when it's high tide, when it's during the flood tide, flow direction gets a little weak, but it doesn't reverse, it keeps its direction. And then when we have hydrodynamic model, we can add quantities, like we can add salinity, for example, and simulate salinity. Here we have fresh water coming from 2 rivers and saline water coming from open boundaries. Or we can have a sediment transport model. I hope it works, yes. So yeah, we see the plume of the rivers. We have sediment concentration. This is concentration of mud in the model. And again, some parts of these sediments will deposit on the delta, and that's how the delta is formed in the first place. And then the flow will erode, especially at the middle of the channels. So we'll have erosion too. So we can finally see that the bathymetry is moving. If you notice, here we are predicting the future 10 years. This is a model that I'm still working on that. As you can see, delta is developing. We are having like natural bifurcation. And this is another way to look at the bathymetry movement. So these are the kind of outputs we can get from a hydrodynamic, sediment, and morphodynamic model. Now let's move on the cases that we are going to run today. We are going to have 4 cases. Case 1 is only flow model, only hydrodynamic. Case 2 is also a hydrodynamic model, but we will add, we will change the Chezy number. We will adjust the friction map of the model to see how it, affects the results. And then in case 3, we will have a morphology model with just 1 sediment fraction, which is sand. And in case 4, we will have, again, a morphology model with 2 sediment fraction with sand and mud. But if we have time, I will add 2 more cases, 2 variants of case 2. Case 2 version 2 is, again, a flow model, a hydrodynamic model, but we will have more boundaries, more accurate boundaries in the model. And also, if we have time, we will add salinity to the model to see the results. Okay, so installing Delft3D. First, how many of you do not have PC? or access to PC. So everyone has access to PC. That's perfect. That's great. Awesome. All right. So I wanted to talk about Windows option, but I guess I can skip this because everyone has access to PC. All right. So before installing Delft3D, it's very important to know that we have two Delft3D models, Delft3D 4. It's a finite difference model, and it works on regular grid, either rectilinear or curvilinear grid. And we also have Delft3D FM. FM is acronym for flexible mesh. It's a finite volume model, and it works on a flexible grid, like a triangular grid. So we are going to work on Delft3D 4 today. Okay, so don't forget that Delft3D is a free model. It's an open source free model. You just need to compile it yourself. You can buy it too, but you can buy the pre-compiled version to, make the life easy if you want. But Delft3D is an open source model, and you have two ways to access Delft3D. You can compile it yourself, either on Windows or Linux. I have done it myself. I've compiled both on Windows and also on Linux to run on HPC when you have like high resolution models. And also you can install a pre-compiled version, which is very easy, just a couple of next on your Windows, and then it's installed. Today we are going to use the second way because compilation process can be challenging and it's time consuming. So Deltares provided us with a pre-compiled version. I think, let me ask this question. Has everyone installed Delft3D? How many of you have not installed? One? Okay, two, because I myself uninstalled Delft3D. So let's go ahead. I just want to show you, if you go to the Deltares website, the password to enter the website is Delta-X. And then we have a page here, Delft3D for Delta-X workshop. Click on terms and condition. And then scroll down, type your name. Or email, and check these two options. You're agreeing with the terms and condition, and then download. So you have three download options. We have Delft3D 4, Delft3D FM. We didn't need that, but they also provided us with Delft3D FM. So I suggest you to, for future, go ahead. That's what I will do myself. I'll go ahead, download this, and start working with the flexible version as well. So yeah, you have now both versions, Delft3D 4, Delft3D FM, and also the license file, which works with both versions. Download for today, we just need the first one and the third one. Download those two. I've done that before. Okay, this is my Windows. I think you are all familiar with this kind of Windows. This is my mini Windows in the Mac. This is Amazon service I'm using. And Mark is paying for that. I think $70 per month, $80 per month. Okay. And when you maximize that window, you are literally in a Windows system. Right, so here is this is the file you download from the website. Just maybe for you that you have not installed. Just extract the folder, right click, extract the file, go to the folder, and you have another zip file probably in that extracted folder. Extract that too. So I've done this before. I have the extracted folder here. and then click on Install Shield. So do you see these windows now? Angelina, I guess. Do you see these windows now? Are you trying to set up? Okay, all right. So I'm going fast because all of you have Delft3D. We are going to skip these two first steps. We don't need them. Then we install License Manager first. Which one? Oh no, that's the different version. Yes, you have to, sometimes you have to have a couple of MATLAB runtimes installed on your Windows system. The default one that Delft3D uses is, I think, 8.2. For Delft3D Dashboard, we need 9.6. So I'm running the License Manager now. Next, 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 next. And I locate my license file here. This is a license file you downloaded during the in the website, in the Delta-S website. Okay, now we install MATLAB runtime. Yeah, I wish I knew I uninstalled Delft3D to teach you what you have. You all have Delft3D. Anyway, it will take just a few minutes, like 4 or 5 minutes to install Delft3D if you have a good connection to internet. So you see this MATLAB runtime is 8.2 Urea. It's 8.2. This is different from the one that we use for Delft3D Dashboard, which is 9.6. Yeah. Okay, you need 9.6 for dashboard. Yes. Okay. But you have Delft3D, right? So we can still work with Delft3D. That's good. And then we need to install Delft3D, obviously. Accept the terms and condition. Next, complete, install. This is where it's installing the binaries. x64. You should have this folder in your computer. And done. Now we have installed Delft3D. You see it's on my desktop. Let's quit the setup. Okay, so this is the main window for Delft3D. I'm going to give you a quick tour. We will come back to this later. This is the main menu of the model. We have information part here. We have a grid part. We make our grid here. We make the flow model and also run the flow model here. And we make the wave model and run the wave model here. And also other parts are for water quality and other stuff. For now, we can quit Delft3D. Okay, so for case one, we are going to run a hydrodynamic model. And hydrodynamic model is based on shallow water equations. We have momentum equation in the x direction, momentum equation in the y direction, inertial forces, advection forces, Coriolis, pressure gradient, external forces like wind and wave come here. And then obviously we have mixing. And at the end, we have the counteracting force, like the bottom shear stress. And also we have advection term here. So it's always good to know what's going on in a flow model. So in order to set up case one, we any case actually in Delft3D, we have two tools. We have Delft3D Dashboard, which is like this, and also Delft3D main menu. For case one, we are going to use Delft3D Dashboard. So this is how Delft3D Dashboard works. You go to your Delft3D Dashboard folder, and you extract your folder, the folder that you downloaded from the instruction file. And then there are two folders in that file, bin and data. Go to the bin, and there is Delft3D Dashboard.exe. That's a standalone exe file. You don't need to install anything if you have installed MATLAB Runtime 9.6. And then when you click on it, it starts working. It takes a few seconds for it to pop up. So we wait for that. In the meantime, I'm coming to you to see what's your problem with Delft3D Dashboard. Okay, so let's start setting up case one. The first thing you do is that you go to the file and select your working directory. That's the first thing we do always when working with Delft3D. So for example, I myself make a folder in the desktop. I call it case one. So again, go to the file and then select working directory. The next thing we do is to define our coordinate system. The default coordinate system is WGS84. That's a spherical coordinate. If I hover over different location, you see that X, Y is in degrees. That's a spherical coordinate. But I prefer to work on a UTM system. So just click on coordinate system, select UTM zone. Again, coordinate system, select UTM zone, click yes. And then I click here and find Gulf of Mexico and find Northern Gulf of Mexico. Choose number 15 on top of Gulf of Mexico. We are going to use UTM zone 15 north. So it will automatically zoom in to the area. It will go to the Northern Gulf of Mexico. And then I usually go to the view. That's where you can check or uncheck things. Yes. Warning about what? Overriding files that exist. Oh yeah, just click yes, because if you are in the middle of setting up a model, you shouldn't change your coordinate system. It will discard everything. We have not set up anything, so it's okay. Just click yes and continue. Yeah. Should we also be doing some empty directory or the one that we downloaded? Just make a folder for yourself. I personally made a folder called case one in desktop, and I selected that as my working directory. And then click UTM zone 15 north. That's because we are going to work on a UTM coordinate system. So I usually turn off shoreline here because the default shoreline does not have enough resolution. And then go to the bathymetry here and choose delta X. So this is the delta X DEM I have added to the dashboard. So we have a very high quality DEM made by our team. Alex was the lead in making this DEM. So I suggest you all, if you are doing modeling, I remember when I was doing my PhD at LSU, the first challenge modelers face is having a good DEM. And at that time, we didn't have one. But now, at least for significant portion of coastal Louisiana, we have Delta XDEM. You can just go to ORNL website, log in and download the Delta XDEM. So the DEM we have is has 10-meter resolution, but in order to be able to use it for the workshop, I reduced the resolution to 50-meter, and now it's here. It's on Delft3D Dashboard. So could you follow me? Are you here? Okay. How to find the D? Okay. So in Delft3D Dashboard, you mean, or okay. So you go to the bathymetry, and then click on delta X, the last option. All right. And then it will take maybe a few seconds, and the Delta XDEM will pop up. So the next thing I do is that I go to the view, and I go to the settings. Again, view, settings, uncheck automatic color limits, and set the limits maybe to -3 to 3. So it's just for, you know, better view of the bathymetry. Again, view, settings, uncheck automatic color limits, and set the limits to -3 to 3. So you can see the bathymetry. Now we are going to make our grid. And how do we do that? There's an option here, draw grid outline. First, we define the outline of the grid. That's the border of our grid. So just click on draw grid line, and then just click and drag maybe a square like this. It doesn't matter because you can modify this grid outline. Again, click on draw grid outline here, and then click, drag, make a rectangular on your area. Just click on draw grid outline, and yeah, do it again. If you made a mistake, do it again. All right. So draw an approximate grid outline. Then you can always click on the corners and adjust your grid outline. Now I'm adjusting my grid outline, you see. And then maybe I want to bring it down a little bit. Yeah. So try to put your northern boundary here on top of these two rivers. We have Wax Lake River here and also Atchafalaya River here. Later we are going to put river boundaries here, so it's better to be here. It's a better place for you know, just for the sake of your boundary position. You can always click on the corners and adjust your boundary outline. Okay, now it's time to make the grid. If you look, we have delta X and also delta Y. That's the size of the grid, and the default size is 100 meter or 1 kilometer. I just need to click on make rectangular grid here. Don't change anything and just click make rectangular grid. And then, oh, we forgot something. Before making rectangular grid, here in run ID, change it to case 1, and also attribute name to case 1. That's just the name of the model. All the files you are trying to save from now on, it will be saved with this name. Okay, so case one, and then click on make rectangular grid, and you see it's saving case1.grd. That's the grid file that Delft3D uses, case1.grd. Just click on that, just save, and you see the grid is here. We have the grid now. It's a 1 kilometer grid. Obviously, it doesn't have, enough resolution for us. So we are going to improve it right now. We are going to up to 100 meter right now. So did anyone make, is there anyone who couldn't make the grid? Everybody could make the grid now? Okay. So now instead of 1000, I just put 100 here. That's the resolution of our grid. We are going to work with a 100 meter grid. And then click again, make rectangular grid, save it. You can replace it with the old one. This is the 100 meter grid, you see. So if you notice, there are areas that you don't have grid. That's because of this criteria here, 0. Can you see this number 0 here? So we have to put a large number there. Basically, we are forcing the Delft3D dashboard to make grid everywhere. So let's put maybe 100 here. And then again, click on make rectangular grid, replace it with the old file. And then you see that the grid is made everywhere. If you want to see the grid, actually, I have to zoom a little bit. That's the 100 meter grid that we are going to work with for case 1. Anybody has questions? Okay. So we made the grid. Always when you make the grid, the second step is to make your bathymetry. And here you can do that just by one click. Click on make bathymetry. It will interpolate all the delta X DEM that we see here, this DEM, to the 100 meter grid. So click on make bathymetry, save it as case1.def, DEP. That's it. We have made the bathymetry. If you want to see the bathymetry, you can go to view, uncheck bathymetry. Again, go to view, go to Delft3D flow and uncheck grid. View Delft3D flow, uncheck grid. Now you see the bathymetry that we just made. We are going to use this grid and also the bathymetry in a file. So we unchecked grid so we can see what's under the grid. We are very close actually to run case 1. We just need to assign our boundary first. So go to boundaries, this tab here, and then maybe zoom to the southern part of your model. Yes. No, I didn't see that. Can you read that? It's both topo and bathymetry. This is what he means. Yes. Delta XDM is both bathymetry and topo. So it has information under the water and also above the water. $10 meter, yeah. Okay. So let's add the southern boundary. You just click on add here, and then drag a line from here to the corner of the island because we don't want, okay, sometimes it doesn't work. You have to do it again. Okay, so draw a line from the left corner to the corner of the island. And you see the name here. Always by default, the name of the boundary is the coordinate of the line, the first point and the last point. We just rename that to south because it's our south boundary. Okay, yes. Okay, so you have to be careful. Your line should be straight because we are having a 100-meter resolution. Maybe it's better for you to zoom a little bit and then try to drag and make your open boundary. Otherwise, you're going to have like a tinted line and it doesn't accept. The boundary should be a straight line. I can help you. Okay. When you did that, we need to save our boundary file. So click on save here and call it case 1 and save. So click save here and call it case 1. It will be saved. So let's review what type of boundary we are using. We are using a water level boundary, and as a forcing, we are going to use astronomic forces. It means that we are not going to use time series of water level. We are going to use tidal harmonics. And I'll explain that later. Yes? So we made our boundary and saved. Don't forget to save your boundary information. And then we are just one step, left to run our model. Then go back to Toolbox here, Toolbox tab. Go back to Toolbox tab and click and choose this TPOXO 6.2. That's a global tidal model. So we are going to use a global tidal model which has solved tidal information for all parts in the ocean. We are going to use that and extract information on our boundary, the boundary that we just made on the southern part of our grid. So it will automatically connect to that model and extract boundary information for us. That's very handy because it doesn't matter. In some areas, you may not have observations to use that as your open boundary. So you can use a global model, extract the information from a global model, and use that as your boundary. I'll click on this. It will take a few minutes for this, and then I'll come to you, Tom. So again, choose TPXO 6.2. You can choose other models as well, but this is faster. For the sake of the workshop, I'm using this. And then click Make Open Boundary Conditions. Save case1.bca. .bca is the boundary condition file. And then click Save. Then you'll see this window, generating boundary conditions. It will take a few minutes, like 3 or 4 minutes. And if you look at the terminal, always you have a terminal alongside the main Delft3D dashboard, you have a terminal. And then you see that it's now downloading fetching component M2, fetching component S2. It's fetching from the Deltares server. It's downloading these components as your open boundary. And we are going to use these tidal harmonics as our boundary. So I'm going to review it again. It's very simple. We just clicked on Make Open Boundary by choosing Make Boundary Conditions, and by choosing TPXO 6.2. So we are done with the boundary condition. We are ready to run the model. But before that, anybody has questions? All right, I'm coming to you. So when you want to make your boundary, here in the boundary tab, this is the issue that a couple of you had this issue. So make sure that you are having a straight line, because in Delft3D you cannot make like, you cannot start from row 1 and end in row 5. And we are having a 100-meter resolution. If you just are a little bit on the top, you are having like a tilted line. That's not acceptable by Delft3D. Try the boundary line to be exactly a straight line from row 1 to row 1. Okay. Now we can run the model actually. Yes, Satya. Mm-hmm. Yes. Let's actually, that's a very good question. Let's check that boundary condition we made. That's a text file, right? We can always open the input files of Delft3D with a text editor. Just click on BCA file. Oh, not this one. Let me delete this. Oh. My working directory is desktop case 1. Click on BCA file. You see, we have south A. That's the starting point of the boundary. And then we have south B. That's the end point of the boundary. And then what Delft3D did for us, that it went to the first point and downloaded amplitude, the first column, and phase, the second column of these major tidal constituents. Obviously, we don't need all of these tidal harmonics because we are located in Louisiana, northern Gulf of Mexico. Tides are diurnal. Just K1, O1, and M2 probably. These three explain 99% of water level variation. So, but no harm, we are going to all of them now. So you see we have M2, S2, N2, K2, K1, O1, P1, Q1. Probably we could just use K1, O1, and also maybe M2, where is M2? Yeah, here, and delete others. But we are going to use all of them now. Okay. So now we go to the description tab here. You see the description tab. This is where you can describe your model, whatever you want. I just write delta X workshop, and then I write maybe case 1. And maybe flow only. And maybe 100-meter grid. That's information for yourself. You can keep it in your model. And then when you wrote your description, go to domain. We don't need to do anything in domain. Already the grid file is imported. The enclosure file is imported. And then go to the time frame. That's where we are going to set our time frame. So set the start time as January 1st, 2024. That's just a round date. We can use that to start our model. So January 1st, 2028. So the start time is January 8, 2028, and we are going to run the model for 7 days. So the stop time should be 8th of January. So we start from January 1st, 2024, and end on January 8th, 2024. So we are basically running the model for 7 full days. And the reference date is not that important, but I always put that reference date the same as my starting date. So set the starting date as your starting time, so January 1st, 2024. And then we need to set our time step. The time step we are going to use for case 1 is 4 minutes. I know it's a little bit maybe high for a 100-meter resolution grid. Our current number, which I will explain later, is maybe a little bit large, but it works for case 1. We need the model to run fast. So let's just use 4 minutes now. And don't forget that the time step unit is minutes in Delft3D. So 4 minutes, January 1st, 2024 till January 8, 2024. And the reference date is January 1st, 2024, the same as your start time. Okay. And then go to processes. This is where you can add processes if you want to add sediment model, if you want to add wind or salinity. We don't add anything now. Just skip this, go to the next tab, initial conditions. We are going to start from 0 initial conditions. So water level is 0 meter at the starting time of the model. So we already were in the boundaries, so we don't need to add anything in the boundaries. Then go to the physical parameters. Okay, now we are in physical parameter tab. We have some constants here. We don't need to touch them. And go to the roughness. So again, we were in physical parameters. And go to the roughness tab. And then for the Manning number, choose Chezy instead. And change Chezy numbers to 65 and 65. So we are going to use uniform Chezy number, 65, 65. Later, we are going to adjust these Chezy numbers and use a specially varying Chezy number in case 2. So Chezy 65, 65, and then go to the numerical parameters. We don't need to do anything here in numerical parameters. Go to the discharge. We don't need to do anything in discharge. And then go to the monitoring. So we are going to add 2 points for monitoring. This is where you are going to get output from your model, the time series output. You can get map outputs, which means that you are going to get outputs in every grid points of your model. We call it map output. And then you can also get time series output. You add points and force the model to give you output specifically in those points. So again, in monitoring section, click add, here add, and click right beside this island. We have an island here, right? That's Eugene Island. Why I'm choosing that point? Because we have Eugene Island, we have a NOAA station there. Maybe we can use that to calibrate our model later. So it's better always to choose, a monitoring station close to your observation points, your tidal gauges. So I'm going to call this one. Again, when you add something in your map, always the default name is the coordinates of that point. I usually used to change it to, I give it a name. I just gave it M1 as the name. Okay, we are going to add a second monitoring station, maybe upstream of the river, so we can compare how is the water level variation in the open water and also upstream of the water. So maybe here is good. I'm going to use, again, click on add, and maybe here in Atchafalaya River, click another point and I call it M2. So we have 2 monitoring stations. One is M1. It was close to the island in the open water, and M2 in Atchafalaya River. And then go to output. And you see in the output, we have a section for map file. This is where model information in every grid point will be saved. So in map file, you see we have a starting point, we have a stop time. You can change it if you want, but I want output from the starting time of the model to the end time of the model. So I don't change anything. And I want output to be made every 60 minutes. So I don't change it here. We don't need to work with communication file. Skip that. And then for history file, I'm going to use maybe 60 minutes. So history file is in monitoring stations. I'm asking model that give me output every 60 minutes in my monitoring stations. In M1 that we just selected in the open water, and M2 in Atchafalaya River. And then that's it. We can just save the MDF file. An MDF file is metadata file. It's the file that connects all of these inputs that we made. It connects all of them together, all the information, it keeps all the information about the model. So go to the file and save MDF file. That's it. File, save MDF file. And if you go to your working directory, you have case1.mdf. That's the one that we are going to use to run the model. All right. Now it's time to run the model. Let's go to, you can minimize Delft3D Dashboard. We don't need Delft3D Dashboard anymore. Open your Delft3D, yes. Oh, yes. That's very good point. We forgot to save our monitoring stations. So let's go back to Delft3D Dashboard. Go to monitoring and save your monitoring stations. Otherwise, you will not get output in monitoring stations. Just call it case one. It's better to be consistent. I name everything case one. And then when you did that, go ahead, go to the file and save MDF file. So don't forget, file, save MDF file. Then minimize Delft3D Dashboard. And then open Delft3D. It's probably on your desktop. Or you can search on your search bar Delft3D. It's here. And then select your working directory. Again, this is the first thing you do when working with Delft3D. And select case one folder. Select folder. And then go to the flow. And then go to the start. Browse your MDF file. Browse your MDF file, click OK. And you see the model just started working. It's going to take 15 minutes to run this model. You see time to finish is 15 minutes. So it's case one, which is running. If you could not follow me, or if you didn't have Delft3D Dashboard, you can download case one input files from the instruction file and open Delft3D, go to the flow, start, and start running the model. I think we have 15 minutes now to answer questions. Anybody has questions? So the point of using Delft3D, because you can set up everything in Delft3D as we are going to do case 2 and case 3 and case 4. The point of using Delft3D Dashboard is that you can use it to set up a model for everywhere. You have like bathymetry files there. Let me show you. So you have different sources of bathymetry here. You don't have this in Delft3D main menu. And then you have, I've added Delta XDM here, which is more convenient for us to work for the workshop. And then, okay, that's, you should go to the toolbox. Let me complete my answer to you. And then you have this fast toolbox here in the Delft3D dashboard that you can literally make your grid and your bathymetry in just maybe less than 5 minutes. I think that's very important. To be able to set up a model just in a few minutes, I think that's priceless. And then you can even make your boundary conditions. It automatically downloads from a global tidal model amplitudes and phases in your open boundary. So it doesn't matter where you are going to run your model. You can always have a model, set up a model just in 5 minutes. That's the point of using Delft3D, and I thought that it's good for everyone to get familiar with Delft3D dashboard. Okay, where you can add that, you can add your own DM always to the 3D dashboard. You should go to the toolbox and go to the bathymetry toolbox. And then click on import. And you see you can have different formats. Probably XYZ is the easiest one. You choose XYZ, you choose the source, the coordinate system of your file. If it's UTM, you select UTM. If it's WGS84, you choose it. And then you add it to Delft3D dashboard, and it's added to your cache, Delft3D dashboard cache, and you can use it. Or you can even share it with others, as I added the Delta XDM, and I shared it with you, and it's working. All right. So I think we are back in time a little bit. Again, if you couldn't follow me making input files for case one, you can download case one and run the model at least. And if you don't want to run the model, we have the output of case one output. I hope you have downloaded that before. So I'm going to just stop this because we have the output already. So I'm going to, we have 11 minutes to finish the model. And I think this is really great because we are having like 100-meter grid in a relatively large area. We have enough resolution to see what's going on in the model. And then it just takes 15 minutes to run the model for 7 days. So let's just close it. Now it's time for visualizing the results. For visualizing the results, we use QUICKPLOT here. Again, when you start Delft3D menu, it's on flow and then QUICKPLOT. But before clicking on QUICKPLOT, we need to change our working directory to case2 output. So select your working directory and go to where you have saved case one output. Case one output. You have probably downloaded this file, right? Case one output. Click on that and then select folder. Now click on QUICKPLOT. Okay. QUICKPLOT is the tool that you can use to visualize your results. Then click on this icon here. This is where you open your outputs, your Delft3D outputs. Click on it. And then you see two .dat files. Those are ASCII files. Those are outputs of Delft3D. And one is called TRIH. H is it shows its history file. It has information just in those two monitoring stations that we assigned. And TRIM, that M is an indicator that it's for the map file. It has outputs in the grid file in every grid points. So first, let's analyze the time series just in those two monitoring stations. Click on TRIH dash case1.dat, this one. And then you have a couple of options. There are different outputs there. Click on water level. Click on water level. Choose all. It should be checked by default. These are the number of time steps that the model has saved output, right? And then I usually come here. I don't like the blue color. Let's change it to black color. So change the color to black and then click on Quick View. That's water level simulated, modeled in monitoring station 1, M1. Now let's add M2 water level variations in M2. So again, remember, M1 was in Eugene Island. It was in open water, and M2 is upstream of the river. So here, change M1 to M2 and change the color to red. And then click on Add to Plot. So what we see here is a comparison of simulated water level in station M1 and station M2. And you see there is a shift in the phase, and we expect that because it takes time for the tide to reach from the open water water to the upstream of the Atchafalaya River. That's because that's why we see this phase shift in the water level. So it's like sanity check. You always check your model if it works or not. We see diurnal variations. We also see semi-diurnal variations, which is smaller compared to diurnal variations. And okay, so 7 days of simulations. We just saw the results in 2 monitoring stations. Now let's see a map of results. Maybe let's see how water level looks like in different time steps in all grid points. So go to this icon again and click the map file, TRIM. That's the map file. Again, we are choosing water level here. All observation. Oh, actually, let's uncheck this all and click on show times. So you can see what times we have output. We started from January 1st, 2024. We have output an hour later. We have an output hour later because we got output every hour, every 60 minutes. And let's choose the last time step. And then scroll down this a little bit. I like horizontal legend color bar. So let's click on horizontal color bar here, and then click on Quick View. Maybe we can zoom a little bit. So that's how water level looks like your last time step. Could everyone see this result? Okay, so now maybe let's make an animation of the results with just the Delft3D tool. Click on this icon here, and then if you want to really save it as a video file, you can maybe choose AVI file here. It will save your video, your animation as an AVI file. We don't need to do that now. We just want to see the animation. So we want to start the animation from time step 1 to the last time step, and then click on continue. So at time 0, everything is 0 because our initial condition was 0. This is time step 3. You see that tide is propagating from your southern boundary into your domain. That's time step 7, 8. That's it. That's you can actually save that AVI file and see it later as a video file. This is how we animate the results. But obviously, we can use other tools like Python or MATLAB. I personally use MATLAB a lot, but this is optional for you because the QUICKPLOT is just for a quick show of the results. It's not publication standard. I don't suggest it for like presentations or for publications. Use Python or MATLAB for processing your results, making animations, making, figures. I'm going to close it. Actually, in case 1 output, I put a folder MATLAB processing. And there is a MATLAB script there. You can use it later to make your animation. It makes a better presentation of your results. The result is something like this. So it's always good to put the time series at 1 point. This is at M1. And also show what are the variations in the second plot, the second subplot. So you have a reference of water level on top, and also you are seeing the results everywhere in your model. So let me run it again. So we just, again, in case 1, we just simulated 7 days of water level variations of the dynamic model, and that's the result. Okay, let's move on to case 2. Okay, in QUICKPLOT, yes, you open the QUICKPLOT, you go to this icon. Okay, so you go to this icon, and you choose TRIM file. So we have 2 outputs in Delft3D. One is for history file, time series file in just monitoring stations, and also TRIM file. That M is an indicator of map file. It has information everywhere in all grid points. Okay, and you can also play with QUICKPLOT. It has a lot of options. Now we are going to move on to the second case. So for the second case, we are going to use Delft3D main menu. So please go ahead, and if you have not downloaded case 2 output, case 2 folder, download it. We need case 2 folder. Okay, let me show you. We need this folder now, case 2. We have all the input files here. Now we are going to set up the model based on those input files. We are not going to make the input files from the scratch as case 1. We are going to use those input files and just import them into Delft3D. Okay. So let's open Delft3D and change your working directory, because now we are going to work on case 2 folder. Select your working directory, go to case 2, choose case 2, and select folder. Okay. Now go to flow input, the first option, flow input. And then go to file, again, open. And open your MDF file here, case2.mdf file. MDF file, metadata file, is the file that has all the information about your model. Choose that one. And let's review what's included in this model that I have set up for you. So we have a description, Delta X Workshop 2024. It's wrong, it's case 2. Let's change it to case 2, the description. Let's go to time frame. Time frame is the same from January 1st, 2024 to January 8th, 2024. Time step is 4 minutes. Let's go to processes. We don't need to add any process now. We are still running a hydrodynamic model. And then go to initial condition. Initial condition is 0. Water level is starting from 0 level. Go to boundaries. You see south boundary there. It's already added. Go to physical parameters. We don't need to change water density or gravity. Those are, known numbers. Go to the roughness. Here is the difference between case 1 and case 2. So in case 2, we are adding a roughness file to the model. Why we are doing that? Because bottom friction is not the same everywhere, right? Bottom friction in the open water is different from in a forest area, on top of the marsh, on top of the delta. So we need to categorize our bottom friction to have better results. And how we do that, we use average NG. Let me go back to my slides. So, okay. So this is a vegetation map that we have made in the Delta X project. My colleague Daniel Jensen has made it. He has used average NG data to make this vegetation map. It's basically categorizing different areas in Atchafalaya and Terrebonne Basin based on the vegetation that we have. Like, for example, we have water, we have forests, we have broadleaf herbaceous, freshwater grass, salt marsh. So we can use these vegetation types and categorize our Chezy number, our bottom friction. There is a link in instruction file to this vegetation map. It's here. It's only 43 megabyte. You can download it. Of course, when you extract it, the size of the file is like one for Terrebonne Bay, it's 1.2 gigabyte. And for Atchafalaya Basin, it's almost 500 megabytes. But log in and download this. It's optional. You don't need to do that now because, as you saw, I have the friction file for you ready in case 2 folder, but I'm going to show you how to do it later. So you download the vegetation map file, and you can use QGIS to make your bottom friction ready for Delft3D. And how do we do that? Anybody works with QGIS? Is there anyone who has not worked with QGIS before? Okay, so I strongly suggest start working with QGIS. It's a free tool based on Python. And you can literally input everything into QGIS, just drag and drop into QGIS, even sometimes model outputs. So these two are vegetation map files that we have made based on average NG data. And you can always click here, go to symbology, see your color bar. So here we see that value of 0 in this raster file is water. Value of 1 is forest. Value of 2 is broadleaf herbaceous. So you can use those values to replace them with, maybe for open water, let's say that I'm going to use a Chezy value of 100. You can change, you can process in QGIS and force QGIS to change all 0 values to 100. So you can use it as Chezy number. Or change all forest is an area that we have a high friction. Maybe we are going to use a Chezy value of 15. Don't forget that Chezy number is always, in reverse order. When we increase Chezy value, it means that we are reducing friction, and vice versa. So let's say that for foresty area, I want to use a Chezy value of 50, a high friction. So I can tell QGIS, replace all values equal to 1 with 50 as a Chezy value. And where you can do that, you can go to the raster. Here, raster, and then raster calculator. And then I have steps in the slides. You will have slides after the workshop. So here are the steps that you can follow after the workshop to make your own bottom friction file based on the vegetation maps. So you can use this line of code in QGIS to basically here with this line of code, we are saying that, okay, wherever in the raster file, which is equal to 1, change it to 0. Wherever in your raster file, which is equal to 0, change it to 100. 0 is open water, and we are going to use a Chezy value of 100. And if the value of the raster file is not 0, then leave it as is. And you can repeat that for all vegetation categories that we have. We have, again, as I said, we have 1, 2, 3, 4, 5, 6, 7, 8 categories in the vegetation map file. And at the end, export your raster file as XYZ file. And you can do that here. You can go to raster and extraction, clip raster by extend, because you may also want to clip your raster file to maybe just Atchafalaya, Terrebonne, or wherever you want to run the model. Define your clipping extent here, and then in the output file, don't forget to save your output file as XYZ file, because you have so many options here. When you save your raster file to XYZ, then you can import that into Delft3D. Again, this was optional. Steps are in the slides. You can follow later. Now we are going to run case 2. Let's go back to the Delft3D. So finally, you will have case 2, RGH, that's roughness file. And this is this file. Actually, I forgot to show this. This is our 100-meter grid we use in case 1. But this is showing Chezy numbers we are going to use in different parts of the grid. And those are vegetation categories. And All right. And then go to numerical parameters. Nothing needed to change. Operations, monitoring, you see M1 and M2 is here. Those are our monitoring stations. And that's it. Let's run the model. Again, close it. You don't need to say yes because case 2 is already set up. Oh, actually, I changed the description. So if you change the description, so then you say yes to all. So you'll save your description. Then go to start and browse your MDF file. Click OK and run the model. Again, it will take 15 minutes to run the model. The only difference between case 1 and case 2 is the vegetation map file that we added to the model. And we're going to see how change in bottom friction changes the results. Let's see what happens. I'm going to stop this. You can run it if you want, but we have case 2 output, right? I think you have downloaded that. So let's go again to QUICKPLOT here. Click on this icon. Actually, before opening case 2, let's close, before opening QUICKPLOT, let's change our working directory. So close QUICKPLOT if you opened it. Select your working directory to case 2 output. You have downloaded this file before the workshop, hopefully. So now go to QUICKPLOT. And again, go to this icon, open your history file, TRIH. Open your history file. And then choose water level here. And choose a station, it doesn't matter. Let's choose a station M2. And then I don't like blue color. Let's change it to black. Quick view. This is your water level variation in a station M2 in case 2 with vegetation map. Now let's add the case 1 so we can compare the results. Again, go to open here, go to case 1 output. Now let's change the color because we want to differentiate between these two. Let's add it as red. And then click on add to plot. So this is the result. You see how water level has changed. With changing friction, with having, instead of having a uniform value of 65 as Chezy number in the model, we use the vegetation map file based on the address NG data. And now the results has changed. And you can use that. You can calibrate your Chezy values based on the vegetation map file and get the correct answer. And what's the correct answer? Antoine is using or has used AirSWAT as a calibration tool for his model. You can use AirSWAT. You can also use field data. We have tide gauges. I'm not sure if our tide gauges are in RNL website or not. They are? No? Yeah. Let me actually show you at least the location of our gauges because we have many gauges. So these are just delta X gauges. If you are doing your research, I think we have more gauges actually, right? These are just few of our gauges. I'm just showing in the Atchafalaya region. So if you are doing your research on the Atchafalaya region, you can use these tidal gauges. And as I said, you can use air SWOT as well to calibrate your model. And also using that vegetation maps to calibrate your bottom friction and get the correct results based on field data or air SWOT. Okay. How much time do we have? 30 minutes? Okay, 13. So we are done with case 1 and case 2. I think we are good. Because we have 13 minutes, let's see what's happening in the extra case files that I made. So let's change your working directory to case 3. No, sorry, not case 3. I think I have not shown you before. Let's go to the instruction file. If you go to the instruction file and go to the test cases, there are 2 more cases here, case 2 version 2 and case 2 version 3. So just download the input files, just case 2 version 2 and also case 2 version 3. We just want to see the input files. I have the output files and I'll show you how much difference we can make in these cases. So case 2 version 2, it's, I don't know, maybe just a few megabytes, just 24 megabyte, download that. And also case 2 version 3. Now, let's select our working directory to case 2 version 2. Select folder, go to the flow inputs. We just did all of this together, so I hope you're following me now. Yeah, it's not responding. Windows takes time. Go to file, open. Maybe for the next session, I'm going to connect to my phone. It's hard to spot my phone. Yeah, but I'm happy that we finished case 1 and case 2. That was the plan. Okay, and then open the metadata file. And then there is a perfect tool here. Go to the view and then click on visualize area. View visualize area. Okay, now let's click on view. It's black because the grid file has 100 million resolution. We cannot see the what's going under the grid file. Go to the view, go to the attribute files and uncheck grid file. So we can see what's going on there. Okay, now I want to maximize this. And then go to colors. Go to bathymetry and change it to rainbow. So what's the difference between this model and case 2? In case 2, we just have one boundary on the south. That was a tidal boundary. In this case, we are adding a west boundary, a lateral boundary. That's the difference. We also are adding our river inputs. You see that Wax and that Atchafalaya. For case 1 and case 2, we didn't add any river discharge to the model. Now we are adding river discharge to the model. Atchafalaya and Wax, and also the lateral boundary. And I'm going to show you quickly how we can add a boundary here. So again, we clicked on view, visualize area. So if you go to the edit, there is an option here for open boundaries. It means that we are editing open boundaries. And then click on edit mode, and then click on delete, because I want to delete the boundaries and add the boundaries right now. Maybe I can zoom a little bit and you can see it better here. So delete, and then just click on it. So I just removed the boundary, the river boundary, Wax Lake River, and I want to add it so you can see. So this time go to change the edit mode to add, and then click here. That's it. You just added a river boundary here. You can minimize this. The newly added boundary is here. Always the name is the coordinates of the first point and the last point of the boundary. But we always change that to, you know, wax. I just call it wax. That's our wax river boundary. So you can add boundaries here. And obviously, I'm telling to the model that this is not a water level boundary. This is a total discharge river boundary. This is a river boundary. And I'm going to use a time series data here. And then you can click on edit flow condition. And I'm going to say that the river discharge is minus 3,500. So always in Delft3D, a negative number means flow is going into your model. Positive means flow is going out of your model. So for river discharge, we put minus 3,500. Why 3,500? This is just a test case. We just want to use a reasonable discharge for Wax Lake Delta to see what's the effect of river discharge in your results. That's it. Let's see the results. How much time do I have? 5 minutes. I want to show you the results. You can just say no because case 2 input files are all set up completely. You don't need to change anything. So change your working directory to case 2 version 2 output. If you have not downloaded case 2 version 2 output, because I just added them last night. So if you have not that, just see the screen. So change your, if you have it, case 2 version 2 output, select it, and then click on Quick Plots. We want to see what's the effect of river on water level in our monitoring stations. Choose your history file, and then change water level. And let's change M2 because M2 is upstream. Monitoring station M2. We want to see what's the effect of river. And quick view. So you see that water level variation is very, it's dissipated. We don't see that much tide there. That's the effect of river. River can choke tides. When we add river to the model, it forces tide not to come in a simple word. So that's the effect of river. Let's actually add the same station water level from case 1 or case 2 and compare them together. So inputs. What? Okay. Exactly. So go to case 1 output maybe, and click the history file. Again, water level M2, change the color to red. And add to plot. Okay, that's how water level in case 1, in which we just had one open boundary in the stars, no river discharge, the red one. And case 2 version 2 looks like when we have river, tide is choked, is dissipated. Actually, you can even look at the field data and see that if that's true or not. I think I had a slide to show that. You see that in observation. If you compare Berwick NOAA station, for example, with Eugene Island station, you see that difference. So these are just these are all sanity check for your model to make sure that your model is working good. If I find that slide, I'm gonna show that to you. So I think we are done. So to wrap up, again, we ran two cases. In case one, we just had a south boundary. Case two, also just a south boundary, tide boundary. We used Delft3D Dashboard to run to set up those models. And we also, using Delft3D Dashboard, we extracted tidal harmonics from a global tidal model and forced that to our open boundary. And the difference between case one and case two was that in case two, we used vegetation map file to, to have a space varying bottom friction. And we saw that the results changed. And in the last case, case two, version 2, we saw the effect of river on water level variations. Now it's time for a break, right? So we'll be back at 10:15.